Yeah, hi everyone. Thanks for coming to our talk. This is my co-speaker Lorenzo. I am Jonas, and we are from TU Freiberg, a technical university in Saxony in Germany. And today we would like to talk to you about the RoverMap framework, a framework we are developing. Its destination is to create, customize, style, and display purely vector data-based digital maps on a variety of platforms. You can see here the acronym. We're not sure if that's the final meaning, rendering optimized vector representation. Maybe you have a better idea, but that's it for now. RoverMap is specialized to display data from an offline data source, so you bundle a little database with your application and load your vector tiles from this database. But we are also working on the classical online workflow with a tile server. RoverMap utilizes low-level 3D APIs to render with full performance. So we use Metal and Vulkan on different platforms. And we are developing a single native code base for rendering in Rust. That's maybe interesting, and I will tell you a little bit more about Rust on the following slides. Yes, but first, a little demo that's from desktop, to be fair, not from a mobile device. And in the end, you will also see a live demo on an Android device, of course. Yes, I will get a short glimpse on the research that's associated with that project. I won't go into the deeps here. RoverMap is the practical or applied part of my PhD thesis, so there's a little bit of research associated with it. That's mostly about the part where you pre-process the geographical data to get into a format that's optimized for rendering. And the actual renderer is more classical software development than research. To go into detail here, you saw the vector tiles on the previous slide, so you have to take the raw geographical data, mostly points, polylines, and multi-polygons, and have to clip them against this tile grid. That's surprisingly difficult because your multi-polygons might be degenerated in the sense that there are intersecting contours, self-intersecting multi-polygons. The inner hole contours might intersect the outer ones, and it's surprisingly difficult to perform intersection in general. And there is an interesting algorithm for that called Watti's algorithm that, for my sense, hasn't been explored enough in literature, so I'm focusing on that part in my thesis. There is also triangulation. You saw we're using low-level 3D APIs, so we need our multi-polygons in triangulated state. We cannot pass the polygons as is, but they have to be decomposed into triangles. And compression is an important part. I told you we are using offline databases for rendering. For example, the federal state of Saxony can be fit into 250 to 300 megabytes compressed, and to achieve this compression is also a part of our research. Yeah, now let's get to the architecture. That's mostly interesting for you, I think. There is a native renderer, one code base in Rust, and it allows us to target all these architectures. So we compile to Android, iOS, macOS, Linux, and Windows from just that single code base in a native way. So no bytecode, no scripting. It's native machine code. Of course, the landscape of rendering RPEs is more fragmented. So there is Vulkan. We have a backend for Vulkan, and it allows us to reach Android, Linux, and Windows. And there is also an initiative called Vulkan Portability from the Kronos group that implements translation layers from Vulkan, for example, to Metal. And that one can be used to target iOS and macOS too using Vulkan. That's pretty interesting. Then we have a dedicated Metal backend that allows to determine the overhead of Vulkan Portability. That's pretty interesting for them, I think. And there is a new kid on the corner, WebGPU. You might have heard of it. It's the successor of WebGL in the browser. And you can also use the WebGPU library in your application. So you don't need a browser. You can use it for desktop and mobile development. And it also has translation layers, for example, to OpenGL ES. We can use that to render on old Android devices that don't support Vulkan. That's pretty neat. Then we can reach DirectX 12. That's also nice. And of course, again, Vulkan and Metal, so we can measure WebGPU's overhead. That's interesting. And there is one more part, because Rust can also be compiled to WebAssembly and WebGPU runs in the browser. We might in the future be able to run our rendering architecture completely in the browser, but there are some showstoppers to that right now. Feel free to ask me if you like to know more about that. Yes, now some words on Rust. I'm not sure if everyone here is familiar with Rust, so I'm giving a very, very short introduction to it. The neat parts about Rust are that it is compiled via LLVM, like Kotlin native, and the Clang compiler, for example. So we get a large number of optimization passes. The code is very fast in the end. The performance is on par with C and C++. We have multi-platform support out of the box, and there is a lot of tooling, especially for the LLVM intermediate representation. Yes, now the neat part, you could ask, why don't we use C++ for that? Rust gives us a lot of static safety guarantees. So all kinds of segmentation faults, memory safety issues, and undefined behavior are virtually gone if you use Rust, and that's pretty interesting. So I brought some code snippet from C++ and the corresponding Rust version on the right. And maybe you can take a look on it if you have ever seen another Rust introduction talk on YouTube. You might be familiar with this sample. It's a pretty nice one. Has anybody an idea what's wrong on the left C++ code? So we are allocating a vector. You know it lives on the heap. We are putting some prime numbers into it, get a reference to the first element, do something with it, push something more to the vector, and print that reference from above. What's the problem? No idea? Yes, behind that? Yes, right. So at this point, we have no spare capacity in our vector, so the heap allocation is full, and this pushback will do a reallocation. So at this point, our reference is dangling, and that's not a good thing. So if we look, for example, in Compiler Explorer and run this program, you'll see we get the reference to the first element. It should be 2, but a 0 is printed, and that's not a good sign. And if we add the address sanitizer library, we can clearly see here in line 14, there is a heap use after 3. So that's a pretty hidden bug there that's not easy to spot. If we are now going back to Rust and analyze this Rust code, there is a thing called a shared reference. It's taken here, this one, and this is read-only in Rust. So you can use it to read the data in the vector at the first point, and you can create as many shared references as you want. But at a later point, we are also creating a mutable reference at this point. And we can deshugger this call, and you see it clearly. This is a mutable reference. And here, the mutable reference and the shared reference live at the same time. And in Rust, this is forbidden. So if we look back to Compiler Explorer and compile the same program here in Rust, we'll get a very nice error message, I think. So the Rust compiler is like, oh, yeah, here in line 3, you're taken in immutable borrow. Then in line 8, there is another mutable borrow. But, oh, no, in line 9, the old immutable borrow or reference is still active. That's not good. Please reevaluate your life choices and change this code somehow. This is pretty bad. So you see the Rust compiler is some kind of Shakespeare of error messages. Sometimes, but sometimes it's also like this. That's not so great. Yeah, little summary of the guarantees that we get from Rust. I told you about that XOR, so maybe n shared references or one mutable reference. You have the choice. That prevents all kinds of data races. We get nice performance bonuses from that. And what's also very nice is move semantics, enforced by the compiler. You might know it from C++11. And automatic memory management via ownership. That means the compiler inserts malloc and free basically for us. No garbage collection, no automatic reference counting like Swift does. It's very low overhead. It's no overhead at all, to be honest. Yeah, and then there is a very important point for our renderer. We also get complete thread safety. So you cannot modify the same variable from two threads at once and get a race condition. That's simply not possible in Rust, and that's amazing. Yeah, now let's talk about Android, and I'd like to focus on the way to get our renderer architecture running in an Android app that might be most interesting to you. We start with some Rust code. This Rust code will create our map, and we are creating a thing that's called a foreign function interface module. Yeah, so you create a special extern C function on the Rust side. So the function conforms to the C ABI. You have to annotate it as unsafe because you're doing some pointer dereferencing in the function. I'm not going into detail. We have to turn off name mangling, and then this function is transformed by a tool called cbindgen, and cbindgen automatically generates a C header for us. And you can see the C header on the right side, and at this point the map struct is opaque, so the C code cannot mess with it. In the next step, we have to install the cross-compilation toolchain for Android. So we have to add all those native targets that Rust compiles to, depending on your Android architecture. And we also need a C or C++ compiler for Android for potential dependencies in C. And so we are requiring the NDK to get this working. Of course, there is helpful tooling, so you don't have to invoke the NDK compilers yourselves. You can use a Gradle plugin from Mozilla, or if you like to do it more manually, there is a nice extension called Cargo NDK to compile for Android. Then step 3, now we are in Kotlin code, so we are writing bindings in Kotlin for our map. There's an internal wrapper class we are calling map here, and map has first to do some static initialization. So there is an external function called map static init. And on the JNI side of the library, in a very little C++ wrapper, we are initializing basically all our JNI references and method references, field references, and so on. Then in the next step, when we want to create a map view itself, there is a map new Vulkan function here on Kotlin side that we are calling in the constructor of our map wrapper. So now back to the C++ JNI. There we are calling the Rust function that you saw on the FFI module slide, our map new Vulkan, and this one will actually create the map. And then we are returning the opaque pointer, casting it to a JLong, and this one is used as handle from the Kotlin side to track the specific map view, so you can have many map views if you like in your application. Then part 5, surface management. So we need a surface for Vulkan to render to. Again, on the Kotlin side, we're creating here some external functions to set and delete the surface. And in our map class, there is a specific function with a nullable surface that sets or deletes the surface. So on JNI, we are taking the surface that's coming in over here and using NDK functions to extract the actual native window from it. And this native window is passed down to Rust. And on the Rust side of things, this is a Rust enum. You're knowing it from Kotlin, where you are using sealed classes. The Swift pendant would be enums with associated values. And in C or C++, it's tagged unions all the way down. And here we are doing a large match or when or case about all our enum types. And there is one for X, one for Wayland, one for Windows, and the one for Android. And if we are using Vulkan portability, we can also target Metal with that. So it's very, very compact multi-platform or multi-AP code down here. In the end, we are creating the actual Vulkan surface that's done down here. And this one can be used for rendering. So now we can throw the whole complicated Vulkan pipeline at this surface. Yeah, and the last step is to create a nice view class in Kotlin for the end user. This is our map view class here, and it wraps the internal JNI wrapper down here. And for example, if the surface is created, this is a subclass of surface view, as you can see here. When the surface is created, we will pass it down to the wrapper, it will pass it down to JNI, and that one will go down to Rust to initialize the map. That's the whole architecture. Yes, and now, Lorenzo, will tell you something more about the high-level parts of our architecture and about styling especially. Thank you.
Okay, so now that Jonas introduced us to the inner workings of our framework, I'm going to take a look at the developer's perspective. What you can see on the left side is a typical OpenStreetMap data collection describing a building with key value pairs. Now we want to take a look how we can render a map from that. The first step is feature selection and feature classification. Here we are defining a feature class and a feature initializer. So at the top, we are first introducing our feature class called building. We then tell our pipeline that we want to render it as polygon and that there should be the properties name and house number. On the bottom, we see the feature initializer. Here we are assigning a debug key so that we can look it up later if something goes wrong. We tell our pipeline that we want to include all OSM features which have the key building in them. And for the actual instantiation, we are referencing back to our feature class name and to our properties. And here we are simply saying that we want to copy the respective values from our OpenStreetMap dataset into our map file. So the end of this pipeline step is just an .RoverMap file, which includes all polygon and all OpenStreetMap data which we want to render. Now the next step is feature styling. Here we are referencing again our feature class from the previous step. We are also telling our pipeline how to render this feature using various colors. And the interesting part here is that our pipeline also supports custom scripting so that we can use our defined properties and construct our label as we want it. Here we are simply looking if name and house number are available. If yes, we both print them, and if not, we are only printing one of them, or none of them if both are nil. So from that pipeline step, we get a style bundle. This is also the part where you can, for example, have a style for light and dark theme if you just set up multiple style files. And in the end, we get this rendered feature, which exactly describes the OSM dataset from the left side. So now that we've seen how our pipeline can be configured, you maybe notice that it might be not trivial to remember all those steps. That's why we want to make this part easier, and we are actively developing a style editor. Here we are using Compose Multiplatform and Docker to make the experience seamless on all major desktop platforms. This very early prototype can already style different OSM polygons, and you can also set up polyline patterns. Of course, we also want to offer Jetpack Compose integration, and for that we heavily relied on the already available Google Map Compose SDK and took many ideas from there. So in the top part, you can see that it's quite easy to set up our RoverMap state, which we then pass to our RoverMap view. And after installing our dependency in our project, which is one liner in our Gradle file, this is all you have to do to get our map working. Inside our RoverMap composable, more or less the magic of all is using the Android view, where we are passing the view you saw earlier into the Android view composable. Now, to sum up our talk, I want to quickly introduce some use cases where our pipeline is already actively used in production. On the left side, you can see a screenshot of our app for supporting firefighters on duty. The main constraints here are that the map has to be fully available offline and that you can have multiple data layers added and removed at one time. Also, performance is really crucial in this context. So at the time of the idea of our project around 2016, none of the available frameworks met all our requirements, so the idea for the RoverMap framework was born. In the middle, you can see a screenshot of our current research project, Steigt where we have a bike rental service. And for that, we also use our map because we want to style our rental stations and manually selected roads in our city to highlight them for the user. And as we are from university and our chair is researching in the direction of human-computer interaction, we also plan to do some research studies, for example, dynamic data visualization on the end device. So now it's time for a demonstration. Yeah, here we can see our map running, and we already see the building which we just set up in our pipeline. If I zoom out, we will see that the map is clipped around the city of Freiberg because this is just the default map of our sample app. Then we have a debug menu where you can already see that the values are updated in real time. And we can also set some properties on our framework, like the tile base size, the multi-sample count, or the scaling factor. So to load a larger map, we just click on this button. And here you can see that the Germany file is about 5.5 gigabytes in size. So we select this file, and instantly we get a map of Germany. You can also zoom into Berlin, and as you can see, up to the smallest details, we've got everything in this single file. So that's all for demo. Of course, you can also come back after our talk to play around with it. And yeah, now we want to thank you for your attention. And if you want to try it out for yourself, we've quickly set up our sample repository only with the Freiberg map. But if you are interested and see use cases for your specific project, please get in touch with us, and let's see what we can do.
And to be fair, I still have to finish my PhD thesis for us to release the code. That's a requirement. I'm sorry, but it will be at the beginning of the next year that all this complete pipeline will be open source. Yes, and we have to add, our chair asked us, we are hiring. So if you're interested in a PhD thesis and some academic research to spice up your CV, then feel free to join us. Thank you.
Thanks.